raise of hands, how many was at my talk yesterday? All right, good. For those who are here, you'll get a little bit of a benefit because I build slightly on that talk. But this talk does stand on its own. It's not a prerequisite. So if you didn't attend, you're all right. I'm going to talk about end-to-end security. And when I refer to end-to-end security, long time no see. When I refer to end-to-end security, I'm referring to client-to-client encryption. Technically speaking, any 2 points in a connection are ends. So I'm not referring to a client-server connection. I'm referring to a client-to-client connection where there's a server sitting between it. So I'm referring to security where the server, the middle server, cannot read, make any sense of, or get any information out of the communication between the two clients. As always, like I said, my slides are under the Creative Commons. If you'd like a copy of my slides, come see me after the talk. Also, we'll see how time goes. I've been timing myself, and it's been right at about 50 minutes. So because I'm the last talk of the day in this room, if you want to hold your questions till the end, I can keep you as long as you'd like answering those questions. But I don't want to keep everybody else late if we don't have to. So with that, here's kind of what we're going to cover. I'm going to talk about information security from a 3,000-foot level. I'll drill in a little bit to what's known as the CIA triad, also known as the AIC triad. It has nothing to do with the Central Intelligence Agency. It's actually an acronym for something else. And then I'm going to build upon some theory on how to successfully create an end-to-end encrypted connection. And that requires talking about authenticated encryption, the cryptographic doom principle, and there's a lot of other stuff in between those topics. And then we'll look at some actual implementations of some end-to-end security applications. So let's start at the 3,000-foot level. Before I even start, I really wish there were dedicated designers to design graphics, because this was designed by someone who was not a graphic designer. I used to work as a contractor for a federal agency, and this sort of stuff would pop up all the time, and I would just have to cock my head and say, I'm not a cryptographic designer, and I could do better than that. But I didn't have time to do better than that, so I had to settle for this. But let's look at this for a second. So our information is at the heart of what we're trying to protect. Our data, it could be a file, it could be a chat, an email. And there are layers that we have to think about in protecting that data. So if we start from the out and work in, our first outer layer is organizational security, also known as our procedural or policy layer. This is things on what to do if, right? Or how to protect, X, Y, and Z. These are things that are documented in wikis, they're documented in in physical format. There's a lot of standards out there, like PCI compliance. For those of you who have to deal with that like I do. There are other sorts of standards out there. These are all policies, procedures that define how to handle securing your information. The middle layer is the people, the persons involved with protecting it. This could be employees, right? Who has access to what? And for those who do have access to that information, kind of going back to the procedure and the policy, how are they supposed to handle it? Are there NDAs involved? Usernames, passwords, so forth. Then that inner ring is the products or the physical security. These are things like firewalls, RFID scanners, NFC chips, physical lock and key. Or this could even be to the software. Certain people have access to SSH to a server, right? So we have some sort of definition in the SSH server who can authenticate and who can't. So these are really our outer rings of our security. When we come in, then we get into what's known as the CIA triad. And it's called CIA for confidentiality, integrity, and availability. And if you'll notice, the availability usually has to do with hardware and software, right? Being able to access the information when it's requested, making sure it's available in a timely manner. This has to do with hardware and software. Where integrity has to do between the software and the communication, whether this is communicated via email, this is communicated via chat, a data file. And then our confidentiality, which we'll talk about, also uses software, but there can be a good deal of hardware involved in terms of protecting that information. This is a better image. This is someone who had an idea of what a clean image looks like. This is the CIA triad. Confidentiality, integrity, and availability. Let's go ahead and define each of those rigorously. So confidentiality we'll define as limiting access or placing restrictions on that information. Right? We're going to put this under the encryption banner, but I mean there are things like not classic, confidential, secret, top secret, right, if you work for the government. These could also be referred to as confidential documents. Even though they might not be encrypted in physical form, there's limited access and there's restrictions on how that information gets used. Integrity we'll define as maintaining and assuring the accuracy and consistency of that information over the duration of its life cycle. As long as that information is available, we should be able to assure that the information is correct. All the bits are in the right order. The data has not been tampered with. It hasn't been corrupted. It's not missing. We can verify with 100% confidence that the information is correct information. Then finally, availability we'll define as that the information must be available when it's requested. Right? And this is where that hardware and software comes into play. We've got to make sure that it's not firewalled away or the database didn't get corrupted or something else. It is available when we need it. I'm going to not really focus much on the availability. This is going to be the last slide I talk about it. But I do want to spend the rest of the time on confidentiality and integrity. So we need to look at a couple more definitions. First, let's talk about encryption. Encryption we'll define as encoding information such that only authorized parties can read it. Really, all encryption is just playing with encoding mechanisms. As silly as this sounds, ROT13 is encryption. It really is, until somebody figures out it's secret. Then the security is no longer valid, right? It's fallen apart. So maybe I compress the data first, convert it to base 64, then do ROT13 on the base 64, right? Until someone has figured out what I've done, that's good enough as encryption. As it sits today, for modern practices, none of those will stand on their own as secure methods for confidentiality on encrypting data. We've got things now like AES, RSA, ECC, a number of other utilities, software, very complex software algorithms. But if you take anything away, all encryption is just encoding the data over and over and over, mixing it up enough to the point that reversing it is practically impossible. Okay? Authentication, however, is keeping information tamper-resistant while also proving that it originated from the sender. Authentication is actually different from integrity. Integrity does not provide authentication, but authentication does provide integrity. You get integrity for free when you have authenticated data. And I'll get a little bit more rigorous about that in the slides. But notice that encryption only provides confidentiality. Encrypting data does not prove anything about its sender or about the consistency of the data. All encrypted data means is it's unreadable for anyone other than those who hold the information or the key or the capability for reversing it, right? And authenticated data only provides data integrity. It does not provide confidentiality at all. It's not within the realm of its scope. There is no encryption as part of authentication, okay? By the way, when I'm referring to authentication, I'm referring to authenticating information, not authenticating individuals. It's a different beast. We're not authenticating users here. We're authenticating the bits that make up that information. Oh, that didn't come out very well. Well, let's see if I can make it smaller. no, bummer. All right, there's a bottom bullet point missing. But that's okay. Confidentiality then. Let's look at confidentiality without integrity. So we're going to look at encryption only, and let's not look at authentication for a second. And let's see what comes as a result. First, confidentiality is vulnerable in the man-in-the-middle attack. This shouldn't be surprising, right? If I wanted to exchange private information between, say, a server and a web browser, if there was no authentication involved, then how do I know that there isn't someone in the middle that's hijacked the connection, acting as a middleman, an active attack that I'm exchanging keys with, and then it's go ahead and exchanging keys with the server, passing the data on and decrypting it in transit. Without authentication, I can't prove that. Okay? So that's one problem. Another problem is, without authentication, I could inject an active attack to send garbage to the recipient or to the sender, and they wouldn't know any wiser. Encrypted data should be indistinguishable from true random noise. That's kind of the point, is we want it to look as random as possible so that it doesn't contain any information, any metadata about itself. One bit doesn't reveal what the next bit could look like, right? So it needs to appear to us as though this is just random noise. Well, what's to prevent someone else from interjecting random noise into the channel? And because I don't have the key to decrypt it, it's just creating problems for me. So without integrity, this becomes a problem. One thing I'm going to show you is something called a CBC bit flipping attack. Yesterday, if you attended my talk about understanding crypto algorithms a little bit better, I talked about block cipher modes. One of those block cipher modes is CBC. In fact, we'll look at that here. Cipher blockchaining. The way this works is I'm going to take my message and divide it into equal-sized blocks. This means that my message needs to be a multiple of that block size. So if I define my block size as 16 kilobytes, or 16 kilobits, whatever, my message needs to be a multiple of that 16 kilobit size. If it's not, this involves what's called padding. I'm going to pad the end of the message with zeros or fives, binary fives, whatever the case may be, until it reaches that multiple size. Then I can evenly divide it into these chunks. So I'm going to take the plain text, and this circle with the plus is an exclusive OR. It's a mathematical operation that flips bits, basically. If you want to get into the details, I'll draw some on the board for you. This initialization vector is a random number. It's the same size as my block size. So if I defined my block size as 16 bits, my initialization vector needs to be 16 bits. We go ahead and exclusive OR the plain text with the initialization vector, take that result and encrypt it with the key, and out pops my ciphertext, the first block of my ciphertext. Then as part of CBC, this becomes the initialization vector for the second block. We do it again, that becomes the initialization vector for the third, so on to the end. Decrypting is the reverse. I take my ciphertext and send it through the block cipher decryption algorithm with my private key. Exclusive OR that with the initialization vector I'd had here, which means the initialization vector needs to be communicated to both parties with the ciphertext. So the initialization vector actually does not need to be private. It can't be private. It's going to be public. It's going to sit somewhere with the ciphertext. Exclusive OR, get my plain text. But notice that my ciphertext is now chained as the initialization vector as part of the second block decryption. So on and so forth until we've worked through the entire ciphertext or the plain text. One interesting thing, let's look at this decryption mode itself. What if I could change one of these bits in the ciphertext in the first block? This is what would fall out. Make that bigger. Maybe I can. So this green box is the bit I decide to flip. Okay? When I send it through the decryption algorithm, I get unreadable plain text. This will be, hopefully, as a result of my, maybe this is AES. this will come out unreadable, corrupted, bad plain text. This will not be what I'm looking for because of that single bit flip. But notice what happens. I carry this over as initialization vector to the next block. Because of the exclusive OR operation, the only bit that gets changed in the plain text is the same bit that I changed in the ciphertext. Why is that interesting? You would think, without understanding fully how encryption works, you would think a single bit flip of the ciphertext would just completely corrupt everything afterwards, right? But knowing how CBC works, we can see that's not the case. It's not going to propagate any further than this. It'll just change that bit. What's the difference between a 0 and a 1 in binary? A single bit. What if this was a browser cookie? And this was authenticating users to a web app, whether or not they had user privileges or admin privileges. And the only way we tell is in the cookie, the encrypted cookie, we have admin equals 0 for false. But if admin equals 1, we let them have admin privileges, right? So what if I can flip the right bit to change that from a 0 to a 1 for the admin? Now they've got administrative privileges in the web interface. This is a CBC bit flipping attack. And it's a very real attack. In fact, how many here are familiar with the, I'm going to say it wrong, the Matisano challenges, the encryption challenges? They were released a year or two ago. Not many. OK, a couple. These are fun challenges. They start very, very basic. Write a simple program that encodes a file into base64. Now write something that decodes it. And you just kind of work your way up until you implement the AES algorithm. And then you implement the AES algorithm with the CBC block mode. Challenge 16 is to manipulate a cookie, an encrypted cookie, to get admin access to a form. So if you haven't tried those challenges, they're a lot of fun. They slowly build on themselves. It doesn't require a ton of math. There's a lot of help online. I'd recommend doing them. And you get to implement this in practice and see how it works. So it's kind of fun. Let's see. Matisano, yeah. Crypto challenges. I'll just do this. Nope. Oh, I don't have internet. The Matisano, I'll write it down. There you go, cryptopals.com. Those challenges are a lot of fun. Like I said, they start very simple. You don't even have to be a master programmer, and they just slowly build on themselves and work their way up. So I hear some snickering. Now I got to get back to where I was. All right. So as a result then, coming back to this, we're talking about confidentiality without integrity, right? Did someone flip the lights on right here? Can we hit them off? Kind of flooding the...
You can adjust them over here on the panel on this wall.
That'll work. All dark now. I apologize to the camera who can't see me.
This one works pretty good for that.
Perfect. Thanks, Dave. I'm crypto competent. I'm not light switch competent. That's right.
Encrypt that light switch, you might get it.
That works. So with this data then, if this ciphertext is not authenticated between the sender and the client, then there's nothing to detect that bit flip. Nothing at all. Right? For my endpoint, when I get the ciphertext, if I don't have anything to verify its integrity, I can't tell anything's wrong with it. Let's just go with it and see what happens. Right? This is a problem. This is why we want authentication. So let's look at confidentiality and integrity without authentication. Remember, integrity does not provide authentication, but authentication does provide integrity. So what's the difference? Integrity says the data is as it was meant to be, right? Someone did a check on this data. You can verify the check, and it comes out clean. Authentication means two parties were involved to negotiate some sort of shared secret, and then they did the integrity check with that secret. So that way, when I get the data from a browser or from a server, not only can I verify that the data is intact, in fact intact, but that it did come from who claimed to have sent it, right? I did the negotiation beforehand. But let's ignore that authentication bit for a sec. Let's look just at the integrity. Here are some vulnerabilities, and I'm not going to outline these each in detail. If you're more interested, come see me after. Vulnerable to a chosen prefix attack or a chosen plain text attack. Vulnerable to a length extension attack. Actually, there's a new cryptographic hashing algorithm that NIST is supposed to finalize on, and there's supposed to be a FIPS standard called SHA-3. You've probably heard the push from SHA-2 from SHA-1, right? SHA-1 is weak. It's not broken yet, but it'll probably be broken tomorrow. Everyone should move off it. The CA authorities are moving off it. Your browsers are now warning you about it. SHA-1 is bad, and SHA-2 is good. Well, SHA-3 was a NIST challenge for the crypto community to build a replacement for SHA-2, just in case SHA-2 got broken. And that became dubbed SHA-3. SHA-3 is not vulnerable to length extension attacks, just as a side note.
Does SHA-3 have NSA backdoors in it?
Nope. SHA-3 comes from a team that developed what's called Ketchak, and Ketchak was chosen as the winner. But it had a large community commenting period and analysis, and yeah.
Before it becomes a NIST standard, won't they put the backdoor?
We'll have to see. Yeah, take that for what you will. You may or may not trust NIST, and I don't blame you. But confidentiality is vulnerable to replay attacks, vulnerable, I got a spelling error, vulnerable to Oracle attacks. This actually shows up quite a bit. And I'm going to talk about an implementation that you're very well familiar with that seems to have a problem with it. So we can get rid of these vulnerabilities by providing authentication. And authentication on confidential information is what's referred to as a message authentication code, or a MAC. Sometimes these are referred to as just tags. This is a MAC tag. And I may refer to it as a tag from here on out. But first off, there's a number of ways we can go about this. Our plain text is going to get encrypted into ciphertext, and then at some point along the way, we're going to digitally sign that text, whether it's the plain text or the ciphertext. That digital signature is what's going to provide that integrity for me. Okay? And we can use hash functions like SHA-1 or SHA-2 or SHA-3 or some others to do this function. But there's three common ways that we're going to do this. We're either going to MAC-then-Encrypt, MAC being the digital signature, right? Or we could MAC and encrypt simultaneously, or we could encrypt then MAC. Let's look at each of these piece by piece and see why we care. First, I guess, and my slide's cut off. It sucks that you have a laptop from 2007 with not a very good resolution that you're developing for, and then you come to a projector that has an even worse resolution. I need to keep that in mind. My laptop is 8 years old. All right. First off, for message authentication codes, this is going to be the authentication. I need the authentication. So the two parties, the parties on either end, are going to agree on a secret. We're going to call that secret K, all right? Then an arbitrary length message, the information that I'm wishing to send to the other end, is going to get hashed with K. It'll either get hashed in plain text or it'll get hashed in ciphertext. Regardless, it's going to get hashed. The resulting fixed length digest, we're going to call a tag, or T, okay? It's important to understand that no matter how large or big this arbitrary length message is, I will always get out the same sized tag. If it's SHA-1, this will be 160 bits in size. If it's SHA-256, this will be 256 bits in size, so forth. This is kind of like a fingerprint, if you will, of the data. It says, I represent this data uniquely. In fact, the digests are commonly referred to as fingerprints. So we have a few, and they're all listed way off the screen, a number of different MAC algorithms. The ones, unfortunately, the one is off here on the slide. The two that I think are probably the most interesting are HMAC, which is a hashed-based MAC. This is what uses SHA-1, SHA-256, SHA-3. Off the screen, there's one called UMAC. This is a universal MAC protocol where I can plug in any hashing function to provide that data. So kind of plug and play. HMAC is usually associated, I'll say HMAC SHA-1 or HMAC SHA-256. But with UMAC, I can specify any cryptographic hashing algorithm. Then there's one way down below the floor called Poly 1305. This is one invented by Daniel J. Bernstein, aka DJB. Some of you may have heard of him. He's a famous cryptographer at the University of Illinois. He invented this as a MAC for a number of different reasons, but it's starting to show up in SSH. It's in the Libra SSL by the OpenBSD developers, and it's starting to pop up in a couple of other places. So let's look at our three protocols: MAC-then-Encrypt, MAC-and-Encrypt, and Encrypt-and-MAC. So first, MAC-then-Encrypt. The MAC is going to be applied on the plain text first. So we're going to hash the plain text. Then we're going to append that MAC tag at the end of the plain text, and we'll encrypt the whole to get my resulting ciphertext. Okay? So we hash the plain text first, get a MAC tag, append the two for encryption, and out comes my ciphertext. As you can probably see, there is no ciphertext integrity. When the ciphertext comes on the other end, I receive this ciphertext. I have no way to verify whether or not the bits have been corrupted or manipulated or they've gone missing until I decrypt it and then use the same hash function on the plain text to check the MAC. If the two MACs equal, then the plain text is good. So while I don't have ciphertext integrity, I do have plain text integrity. MAC-then-Encrypt is used in OpenSSL for your SSL communications between your browser and the web server, or your email client and the email server. However OpenSSL is being used, it uses MAC-then-Encrypt. Turns out this is a problem. We'll talk about it in a sec. Then there's Encrypt-and-MAC, or MAC-and-Encrypt. This is where the plain text is not only hashed, but it's also encrypted at the same time. Then the resulting plain text MAC is appended to the end of the ciphertext. As you can see, again, we don't have any ciphertext integrity. That MAC tag applies only to the plain text. So I first need to decrypt the ciphertext, then check the MAC tag, again by hashing the plain text, getting a new tag, and then verifying if the tags equal each other. Okay? Interestingly enough, this is used in OpenSSH. And it had a problem. So we'll talk about that in a second. Oops. Finally, Encrypt-then-MAC. Encrypt-then-MAC is where I encrypt the plain text first, then I hash the resulting ciphertext, and I apply the MAC tag at the end of the ciphertext. As you can see, I now have ciphertext integrity because that MAC tag is the fingerprint of my ciphertext. So when I get the ciphertext, I can hash the ciphertext and see if the two MAC tags match. If they don't, I don't have to bother with decrypting this. Something happened along the way. It's not going to decrypt cleanly. I'm not going to worry about it. But if they do match, I can go ahead and decrypt the ciphertext and get back to my plain text. So because I've hashed the ciphertext, not only do I get my ciphertext integrity, but for free, I get plain text integrity too. There should be only a one-to-one relationship between the plain text and the ciphertext. So if I can verify that the ciphertext is solid, I get the plain text as solid for free. Make sense? As a result of having both the ciphertext and plain text integrity, This has become defined as an international standard. There's the ISO number. And interestingly enough, this is the default in IPsec. All right, let's talk about the cryptographic doom principle. I forget the, no, it's Moxie. I forget his first name. He defined this principle, and he says that you are doomed if you do anything other than encrypt, then MAC. If the first thing you're doing is not verifying the integrity of the ciphertext, you're in trouble. And he lists two very common examples of what happens, one with encrypt and MAC, and the other with MAC-then-Encrypt. With MAC-then-Encrypt, first off, we're vulnerable to a padding oracle attack. If I go back to my slide here, because the MAC tag is a part of the plain text, and I get my ciphertext, I'm not sure how much the plain text has been padded. So as a result, what I can send to the server is a guess on where the padding is. And I'm going to get one of two errors. I'm either going to get a padding error, or I'm going to get a MAC error, a MAC tag error. Using this information, I can actually be clever about the way I submit my data to the server and decrypt the ciphertext without the key. If you want some cool YouTube videos, at DEF CON, there was a live running example of an SSL connection using MAC-then-Encrypt with OpenSSL, where he could live decrypt the data without knowing the RSA private key. Okay? This is a big threat. And because of the padding oracle attacks, anyone remember Poodle from last year? The sysadmins in us? Poodle is a padding oracle attack. And what it required was downgrading your SSL connection to SSL version 3.0. As a result, the thing to do is to say SSL 3.0 is now insecure. It's time to disable it by default. But the year prior, there was in February 2013, there was the Lucky 13 attack, another padding oracle attack. This is because OpenSSL decides to MAC-then-Encrypt. I promise you, Poodle will not be the last padding oracle attack against OpenSSL because they chose MAC-then-Encrypt. With a MAC-and-Encrypt, however, there was an OpenSSH up to version 5.1, a plain text recovery attack, where you could recover the plain text using weaknesses in the MAC-and-Encrypt protocol. So really, the cryptographic doom principle tells me that unless I am doing encrypt, then MAC, I'm setting myself up for problems. Right? I'm setting myself up for doom. So here is my suggestion. I would encrypt, then MAC. So here's our encrypt, then MAC algorithm, right? Here is verifying the encrypt, then MAC sequence. I receive my ciphertext with the tag. I'm going to break the tag off and hash the ciphertext. I'll get a new MAC tag. So I could say this is tag 1, this is tag 2. Do these two equal each other? If they do, I can go ahead and decrypt my ciphertext and get my plain text. If they don't, I don't have to do this step, right? So the first thing I'm doing before anything else is verifying if these two MACs exist. There are a few ways you can do this. The first is to use what's called AES in GCM mode. This is Galois counter mode. This is a block cipher mode similar to CBC with built-in authentication. I don't have to worry about doing authentication separately after I've done the CBC mode. So using GCM and AES, I get this for free. Another one, also by Daniel J. Bernstein, is the ChaCha20-Poly 1305. ChaCha20 being the encryption, the symmetric encryption algorithm, and then as mentioned earlier, Poly 1305 being the MAC algorithm. Okay? Again, this is showing up in SSH. It's in LibreSSL. It's in libsodium. It's starting to become the new hotness in crypto circles. But if I wanted to do things manually, then I would recommend using either AES with HMAC SHA-256 or SHA-512. SHA-512 is just doing it because you can, not because you need to. Or using AES and SHA-3. With SHA-3, because it's not vulnerable to the length extension attack, you actually don't have to use an HMAC associated with it. So you could just encrypt it with AES and then hash it with SHA-3 with the shared secret, and you automatically have your authenticated data. Again, though, SHA-3 isn't finalized by NIST. It's not quite yet a FIPS standard. So that's the suggestion. So that's the theory behind getting set up or getting ramped up for an end-to-end encrypted communication to keep anybody out from manipulating data like a CBC bit flipping attack, to keep anyone from sending digital noise or random data on the wire to confuse me or piss me off, right? We've set up all the necessary pieces to have confidentiality and authentication completely and totally on the wire. All right. So with that said, let's look at some implementations. The first is off-the-record messaging. Who here is familiar with OTR? Keep your hands up. How many use it? If you drop off, that's all right. OTR is an end-to-end encrypted communications protocol. It can actually be attached. It's completely disconnected to any legacy messaging format like ICQ or AOL Instant Messaging or Jabber or IRC. As long as there's a plugin for the client or the client supports it natively, you can have end-to-end encryption with OTR. It is AES 128-bit encrypted, so there's my confidentiality. And then the data is hashed with SHA-1, which gives me my integrity. There's a couple other fun things about OTR. When Ian Goldberg invented the protocol, at the time, people were using their GPG keys for end-to-end encryption for chat messages. He saw this as a problem. And the problem he saw was GPG, by default, cryptographically signs with your user ID, with your own personal GPG key, all of the messages. What this does is non-repudiates the data. It means that I typed the data, I signed it, I sent it, and nothing else can disprove that. This is a problem if you're a journalist wanting to whistleblow. You may not want that data to be associated with you, right? So we need the ability to strip signatures off, in other words, have an off-the-record conversation, but still have this confidentiality and this authentication. So the way this works is instead of using GPG, we use AES natively, and we use temporary per-message AES keys. This means that, first off, OTR is a hybrid system. It uses public cryptography and symmetric cryptography. Both users will generate a public-private key pair, and they'll swap public keys. Okay? So then we both have a copy of each other's public key. We will generate, one of us will generate a secret with that public key for that message and encrypt it for that other person's public key to send it off to him. We now both have a copy of that AES key. We encrypt the message with the AES key and send it off. But the next message gets a new AES key. We don't keep that AES key encrypting all the messages for the duration of the session. Every time a new message is sent, a new AES key is generated. It's encrypted with the other person's public key, sent off, and then it's encrypted with that AES key. What this provides is something called forward secrecy. Little nitpick. If you refer to this as perfect forward secrecy, you're technically incorrect. Perfect forward secrecy is similar, except for it's not deterministic. In this manner, we are generating deterministic AES keys. So it's not perfect forward secrecy, it's just forward secrecy. If you want more info, you can read about it on Wikipedia. But what forward secrecy provides is for each message I sent off, no previous messages can be decrypted if one of those keys gets compromised, right? So if I sent off 10 messages and the 11th, an attacker is able to grab that AES key, he cannot decrypt the previous 10. He might be able to decrypt the 11th, but he won't be able to decrypt the previous 10, and he won't be able to decrypt 12 forward. Okay? So that's forward secrecy. And then that deniable authentication is where messages are not signed by any sort of user ID. It's not attached to you. So this becomes a problem. How do we get our authentication? SHA-1 just provides the integrity, but how do we get the authentication? How do I know that I'm chatting with Dave and Dave's chatting with me, and I'm not chatting with some evil impersonator? Okay? So the way we do that is something through the Socialist Millionaire Protocol. The Socialist Millionaire Protocol is a generic way of saying, I can tell who's richer between Dave and I without either one of us revealing our salaries, okay, or our income. And the way it works is basically I say, well, I'm pretty sure I'm talking to Dave, but I need to ask Dave a question that only he would know the answer to, that everyone else in this room would not have a clue on how to answer. If he answers correctly, I know I'm talking to Dave, right? And the reverse is true. He'll then ask me a question that only I should have the answer to. If I answer correctly, he knows he's talking to me. Now we've authenticated. Now we can move forward. Authentication isn't required for OTR, but it is strongly encouraged. Unfortunately, OTR does not support group chats, and it does not support audio or video. So it's one-to-one text only. But there's awesome OTR support. There's OTR support for Windows clients, Mac OS X clients, GNU Linux clients, BSD clients, Android clients, iOS. And here's just a number of different clients supported. For native clients, there's Adium, Bittleby, ChatSecure, Cryptocat, so forth. Xabber, I'm not sure how to pronounce this, if it's Xabber or Zabber, yeah, is an Android client that supports OTR natively. Via plugin, Gagem, Ursi, Pigeon, Psy, WeChat, so forth. So if you want OTR, it's very likely that your client probably supports it. Unless you're using like MSN Messenger or like native ICQ, you might be out of luck. So here's an example of Cryptocat. And I took a screenshot. This is actually running on my, I tried taking, there's only one screenshot I didn't take because I couldn't get it installed correctly. But this is running on my Chromium browser. And I joined the lobby channel on Cryptocat. And I took this user, Jax, and this down arrow, I said, view as info. So interestingly enough, Cryptocat was able to get group conversations with OTR. And the way it works is the OTR, or the channel itself, presents itself as a regular user, a nameless user, that everyone is chatting to, and then the nameless user repeats that message to everybody in the room. Okay? So it's still technically one-to-one. They're just kind of working around it to make it work. But it works pretty well. So there is a group fingerprint of the public key for this channel. But what I'm more interested in is the OTR fingerprint for Jax, which is this 08898 blah, 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 blah. Okay? This is the unique fingerprint for this user, Jax. What's interesting is when Jax disconnects and come back, this will be different. Cryptocat generates a new public-private key pair every time you connect. Okay? And then you'll see here, it says this user's identity has not been validated. Answers must match exactly. I can type in my secret question, provide the answer, click ask. He'll get asked the question. If the answer doesn't match what I provided, we didn't authenticate. If we did, I can now verify that this Jax is the Jax I want to talk to and no one else. So.
Also, the Socialist Millionaire question is actually a question I would actually ask, not some technical.
Right, yeah.
Okay.
Yeah, exactly. It'd be like maybe we met before the conference and I said, the secret code word is, right? And then later in the afternoon during lunch, I ask you, what was the code word I gave you this morning? Yeah. Or it could be maybe, pardon?
Spelling counts.
Spelling does count, and so does case. Letter case counts, yes. So sometimes it's helpful to say, you know, what did I tell you about my wife this morning? All lowercase letters, It's like to give them hints on how to proceed with the answer without giving them hints on what the answer could be. So that's helpful. So anyway, Cryptocat is free software. Yesterday I wrote a backwards S on the board. That was interesting. Cryptocat is free software. It's GPL licensed. It's a browser-based client. It runs in the browser. And it's written in JavaScript, fully 100% in JavaScript. It's all client-side. It does connect to a server. The server software is also free software, and you could run a Cryptocat server on your own personal box, on your own infrastructure, and you can change the settings in the client on which server you wish to connect to. So you could have one internal to your company LAN that isn't available externally, as an example. Interestingly enough, Cryptocat has had some security problems in the past. They've corrected it. And I think for the most part, most people will agree that it is secure now, but it has had previous problems. However, the source code has been independently audited by a third party. This is big. Lots of people don't really take source code auditing seriously. But this shows that here's a third party, unaffiliated, unrelated to the project, that went through the source code with a fine-tooth comb, maybe involved some mathematicians or cryptographers, and then found the following results from the source code. Okay? The audit came through favorably. So Cryptocat, despite its history, is a decent OTR client. Here is WeChat. This is an IRC client, a text-based IRC client. They have an OTR plugin written in Python, and it supports the Socialist Millionaire protocol. It has a per-user policy config, so I can say always trust from Landon or always distrust from somebody else. Turn logging on, turn logging off, so forth. However, it only supports OTR protocol version 2. And OTR protocol version 4 was just recently released. So I'm not going to say it's a bad thing. It's certainly not insecure, but there might be maybe some performance improvements that you would see in version 4 over 2. Maybe some better state handling and so forth. But in this case, I'm having a private chat on IRC with this guy named Landon, and I just ran an OTR status to show what my fingerprint is, what his fingerprint is, and we've been verified. I have verified Landon's authenticity. I am chatting with the Landon I expect to be chatting with. Okay?
Do both sides have to be using the same version of OTR?
Nope. That's a good question. If Landon, that's a good question. I'm not entirely sure. We'll have to look at that. Let's come after and we'll look at that. I'm not sure if there's backward compatibility or not. I know in this case that Landon is also using WeChat and he's also using the same OTR plugin, so we don't have a problem there. But if I were to chat with somebody else, I don't know how that would work. So, all right, OpenPGP. OpenPGP is a protocol. It's an RFC. It is not an implementation. OpenPGP is not something you install on your system. Okay? OpenPGP is equivalent to like the private networking address space of IPv4. Right? It defines things, but it's not the TCP stack or the IP stack on your system. So here are all the RFCs that OpenPGP is defined in. OpenPGP is really unencumbered PGP. PGP is pretty good privacy that was developed by Phil Zimmerman in 1991. And it had some patented algorithms in it. OpenPGP was saying, let's build a PGP-compatible system without those patented algorithms. And so the original PGP message exchange format is an RFC 1991. The rest are OpenPGP standards in the rest of those RFCs. And they're defined here. But there is an implementation of OpenPGP, and that's the GNU Privacy Guard, or GPG. GPG is a command line-based client. It's maintained in 3 branches. It's funny how you go through your slides with a fine-tooth comb and you miss stuff, right? There are 3 branches. There's the stable branch in 2.0, modern in 2.1, and classic in 1.4. There are different versions. Modern in 2.1, for example, supports ECC, elliptic curve cryptography, where the other 2 branches do not. It is a hybrid encryption software, which means it is a public key system. I generate a public-private key pair, give everybody a copy of my public key. But when I want to do encrypted emails or encrypted chats with GPG, what's going to happen is I'm going to generate an AES key, encrypt it to the recipient's public key, so he has a copy of it, and then we'll just use that symmetric key for the encryption from here on out. The reason why symmetric encryption is far more performing than public key encryption. Public key encryption is a beast on the CPU. It just doesn't scale. So we use symmetric encryption when we actually want to do the encryption. So here's some support on the public key. It supports RSA, LGAMO, and DSA. For the symmetric ciphers, those are listed here, AES, Blowfish, so forth. For the cryptographic hashes, these are listed. Notice that SHA-3 is not on that list. It's not defined in OpenPGP yet. And then beneath here, there's compression support for uncompressed zlib and bzip2. GPG support has support on Windows, OS X, GNU Linux, BSD, Android, iOS. There are all sorts of third-party GUI front ends, right? There's KGPG, there's GPA, there's GPG tools for Mac, GPG for Win for Windows. Mutt supports GPG natively. Mutt is a text-based mail client, so on and so forth. So there's a lot of utilities that support GPG that you can use for your end-to-end encryption. It is a little bit of work, and it is a little bit of maintenance, though. For those of you who have GPG keys, probably very aware of the web of trust and key signing parties and keeping your key up to date and public key servers, and the list goes on. This is not a trivial thing, but it's a very strong thing. In fact, recently at DEF CON, the last DEF CON, it was released that the NSA had a problem decrypting OTR and GPG messages. But they could decrypt some SSH and some SSL connections. So that's promising. Pardon?
Is that just because of the attacks that you mentioned before?
Yeah, some attacks, like the padding oracle attacks. Also, the ability to downgrade, in the case of SSL, downgrade to what's called an export mode, where everything is in 40 bits instead of the stronger bits because of the USA cryptography export laws that were relaxed when Bill Clinton was president. There's some other things. But yeah, an improperly configured SSL or SSH was within realm of decryption for the NSA. But OTR and GPG was out of reach. A couple others that we're out of time. I'll just go through these quickly. Tox, if you're not familiar with it, is designed to be a Skype replacement. It's fully decentralized. It's peer-to-peer. It uses the BitTorrent dynamic hash tree protocol, the DHT protocol, for network traversal. But it supports text, single group chat, as well as video chat. I use it quite a bit. Works really well, actually. The architecture is separated into a core library, the protocol, and the clients, so it's trivial to, or flexible, I should say, to design your own clients. What's interesting, though, is it uses libsodium for the crypto library, which is designed by DJB. So instead of using AES and SHA-1 and more of the industry standards, it uses curve 25519, which is an ECC curve for the key exchange rather than RSA or Diffie-Hellman. It uses Xsalsa, not Salso, Xsalsa 20 for the cipher, and then it uses Poly 1305 for the MAC. Unfortunately, there's not been an independent security audit. Here's a weak screenshot. I didn't know what I wanted to show. So here's my Tox user ID. I'm in a group chat. Unfortunately, my user ID for Tox is rather unwieldy, and that's how they all are. So this isn't something you say, oh yeah, my Tox ID is 135FF76. No, this is something you send via email or text message so they can copy and paste. What?
Hence the copy button.
Hence the copy button, yep. That's actually got a bug on GitHub about how to change the Tox ID to something a little bit more usable. Bitmessage. Bitmessage is a email-like replacement, again, fully decentralized, fully peer-to-peer. It uses public key encryption and decryption entirely. There is no symmetric encryption with Bitmessage at all. The main client is written in Python. And when you send a message, because it's peer-to-peer, there's actually no metadata in the message, the encrypted message at all in plain text. So when I write an encrypted message, say, that's meant for Trevor, it actually gets broadcast to every node on the network. Every node attempts to decrypt it. Unless you have that private key, though, you're not going to be able to decrypt it. The only one who has the private key, which hopefully should be Trevor, can. So Trevor would be the only one that'd be able to read the message. So it's broadcast to every node. It does require a proof of work. There's a proof of work system similar to Bitcoin, similar to Hashcash, that your client must solve, a puzzle that it must solve that's CPU heavy before the message can get sent off to the network. Interesting Bitmessage addresses are similar to Bitcoin addresses, and they're also backwards compatible with Bitcoin keys. Messages are not archived on the network, but each node does store them for a couple of days. Here's a Bitmessage screenshot of me going through a few of the channels. Bitmessage does have one-to-one messaging, but it also has like mailing lists and what it calls channels, where everyone can join the channel, but everyone gets a copy of not only the public key, but the private key to that channel too. So everyone can send messages pretending that they're the channel owner to everybody else on the channel. So it does make for some unruly discussions because it's fully unmoderated, but interesting nonetheless. Finally, RetroShare. RetroShare is kind of a large, monolithic, end-to-end encrypted system for file sharing, serverless email, kind of like Bitmessage, instant messaging, chat room, even BBS support. I really should have gone through these slides in a more fine-tooth comb. Data at rest uses OpenPGP, so it uses on-the-fly sacrificial PGP keys, GPG keys. And the network communication is all used with SSL. It uses the BitTorrent DHT for its network traversal, similar to TOX. There's some of the encryption stuff about it. Also, no independent security audit. And here's the screenshot that I had to steal from the internet because I was having trouble with my install. So those are some 5 implementations: OTR, GPG, TOX, Bitmessage, and RetroShare that you can use right now for end-to-end crypto, whether it's video chat, text messaging, email, file share, so forth. Any questions, comments, rude remarks? Yes, Nick.
Why didn't you cover Curve CP?
Why didn't I cover Curve CP? Are you referring to the NIST curves, or?
I'm talking about Dan Bernstein's protocol to replace, web pages.
Didn't think about it, to be frankly honest.
Okay.
I think some of the Dan Bernstein stuff, like the Poly 1305, the EC 25519, and the Salsa 20, Cha-Cha 20 are interesting, but they're not widely accepted yet, so they're still kind of working their way out. So another question, yeah.
Back to the vulnerabilities you mentioned with SSH and SSL.
Uh-huh.
Are the developers considering doing?
They're not. So that's specific to OpenSSL. If you install PolarSSL or LibS, I think LibSSL also uses MAC-then-Encrypt. But if you install another SSL implementation, it might be different. But in the case of the SSH developers, they're using MAC-then-Encrypt. They're not moving off. They did plug that vulnerability in OpenSSH 5.2. And there hasn't been a MAC-then-Encrypt vulnerability in SSH since. And that's almost 8 years now. So that's good. But no, they're not. They're fine with where they are despite industry best practices, despite the warnings. And the SSL the OpenSSL developers are few and far between. And to rework OpenSSL to do Encrypt-then-MAC would be a major underhaul. It wouldn't be a trivial thing. So I don't see that one happening anytime soon, unfortunately.
Aren't you able to set that in like the OpenSSH config though, which one it uses?
For Mac, you mean like the MAC-then-Encrypt?
Yeah.
I'm not sure. I haven't heard of that.
I thought you could choose to use just like AS.
You can change your cipher and you can change your MAC algorithm, but the way your plain text and ciphertext are handled is a MAC-and-Encrypt. So even though the MAC algorithm and the cipher algorithm change, it still uses a MAC-and-Encrypt protocol. Yep. Any other questions? Nope. All right, if you have any, come see me after.